Artificial gravity is one of the most fascinating and challenging aspects of space exploration. For decades, scientists and engineers have dreamed of creating environments that simulate the gravity of Earth or other planets, allowing humans to live and work comfortably in space. However, the cost and complexity of building and launching artificial gravity systems have been prohibitive, limiting their use to small-scale experiments or science fiction scenarios. That is, until now. Thanks to SpaceX's Starship, a revolutionary launch vehicle that aims to provide low-cost and reusable access to orbit and beyond, artificial gravity systems are becoming more feasible and affordable than ever before. Starship is designed to have a payload capacity of 150 tons, or 330,000 pounds, to low Earth orbit in a fully reusable configuration, and 250 tons, or 550,000 pounds, when expended. This means that Starship can deliver large and heavy structures, such as rotating habitats, centrifuges, or tethered modules, that can generate artificial gravity by spinning or accelerating. For example, one possible way of creating artificial gravity in space is by utilizing a technology called an O'Neill cylinder. Named after the physicist who proposed them, Gerard O'Neill, this consists of a pair of massive cylinders that rotate in opposite directions, allowing them to be permanently directed toward the Sun, replicating gravity. By reducing the cost and increasing the capacity of launching large and heavy structures into space, Starship is opening up new possibilities and opportunities for creating artificial gravity environments that can benefit humans in various ways. Whether it is for exploration, colonization, tourism, or research, artificial gravity systems can enhance our experience and understanding of space. Artificial gravity can help SpaceX succeed with its deep space plans with the Starship. But why exactly is gravity so important in long-distance space travel that it has to be artificially created on the Starship? To start with, gravity affects not only the physical and mental health of humans, but also the performance and safety of spacecraft and equipment. One of the benefits of gravity in deep space travel is that it can help prevent or reduce the negative effects of microgravity on the human body. In fact, not having gravity in deep space travel can pose a serious health risk for astronauts. You might not know it, but gravity is essential for maintaining the normal functioning of the human body, and its absence can cause various physiological and psychological problems. One of the health risks of not having gravity in deep space travel is muscle atrophy. Muscle atrophy is the loss of muscle mass and strength due to disuse or inactivity. Without gravity, astronauts do not get to use their muscles as much as on Earth, and their muscles gradually weaken and shrink. This can affect their ability to perform tasks, such as walking, lifting, or operating equipment. Muscle atrophy can also increase the risk of injury, fatigue, and pain. To prevent or reduce muscle atrophy, astronauts are usually made to exercise regularly and use resistance devices, such as elastic bands or springs. Another health risk of not having gravity in deep space travel is bone loss. Bone loss is the decrease of bone density and quality due to reduced mechanical stress. Hard as it might be to imagine, without gravity, astronauts do not experience the normal weight-bearing forces that stimulate bone formation and maintenance. As a result, their bones lose calcium and other minerals, making them more brittle and prone to fractures. Bone loss can also lead to osteoporosis, a condition that causes bones to become porous and weak. To prevent or reduce bone loss, astronauts need to consume adequate amounts of calcium and vitamin D, as well as exercise with devices that apply force to their bones, such as treadmills or bikes. A third reason SpaceX astronauts have to care about gravity in deep space travel is fluid shifts. Fluid shifts are the redistribution of body fluids from the lower to the upper body due to the lack of hydrostatic pressure. Without gravity, SpaceX astronauts will not have the normal downward pull of blood and other fluids in their legs and feet. Instead, their fluids move upward to their head and chest, causing swelling, congestion, and increased pressure. Fluid shifts can affect various organs and systems, such as the heart, lungs, brain, eyes, and ears. For example, fluid shifts can cause cardiovascular changes, such as increased heart rate and blood pressure, respiratory changes, such as reduced lung capacity and oxygen uptake, neurological changes, such as headaches, dizziness, and nausea, visual changes, such as blurred vision and eye damage, and auditory changes, such as hearing loss and ear infections. But there are even more risks. You also have immune system dysfunction. Immune system dysfunction is the impairment of the body's ability to fight off infections and diseases due to altered immune responses. Without gravity, astronauts experience changes in their immune systems that make them more susceptible to illness and inflammation. For instance, without gravity, astronauts have reduced levels of white blood cells, which are responsible for defending the body against pathogens, increased levels of stress hormones, which can suppress immune function, and altered expression of genes related to immunity. Immune system dysfunction can increase the risk of infections, allergies, autoimmune disorders, and cancer. Yet another health risk of not having gravity in deep space travel is psychological stress. Psychological stress is basically the mental and emotional strain caused by challenging or demanding situations. Without gravity, astronauts face various sources of stress that can affect their mood, cognition, and behavior. For example, in an environment without gravity, astronauts have to cope with isolation, confinement, boredom, monotony, uncertainty, danger, and separation from family and friends. They have to adapt to a new and unfamiliar environment that lacks natural cues and stimuli. They have to deal with physical discomforts and inconveniences caused by microgravity. They have to perform complex and demanding tasks under high pressure. They have to manage interpersonal conflicts and cultural differences with their crewmates. They have to deal with communication delays and technical failures. Psychological stress can lead to anxiety, depression, memory loss, attention deficit, and impaired judgment. Meanwhile, it is not only because of health risks that SpaceX needs to ensure the Starship has gravity in deep space. Another benefit of gravity that SpaceX will gain in this kind of environment is that it can enable more efficient and diverse propulsion systems for spacecraft. Gravity can be used to accelerate or decelerate spacecraft by using gravitational slingshot maneuvers, which involve using the gravity of a planet or a moon to change the speed and direction of a spacecraft. This can save fuel and time, as well as allow access to more destinations in deep space. Gravity can also be used to generate electricity for spacecraft by using gravitational potential energy, which is the energy stored in an object due to its position in a gravitational field. This can provide a renewable and clean source of power for spacecraft in deep space. Yet another benefit of gravity in deep space travel is that it can offer more opportunities and challenges for exploration and discovery. Gravity can create interesting and diverse environments in deep space, such as planets, moons, asteroids, comets, and rings. These environments can have different features, such as atmospheres, climates, geology, biology, and culture. By exploring these environments with gravity, astronauts can learn more about the origin and evolution of the solar system and the universe, as well as search for signs of life and civilization. However, astronauts have to be careful because gravity can also create obstacles and dangers for exploration, such as gravity wells, tidal forces, orbital debris, and meteoroids. These obstacles and dangers can test the skills and courage of astronauts, but the upside is that they can inspire new technologies and solutions. So yes, gravity is a big deal in space travel. However, how can SpaceX introduce gravity where it doesn't exist on a spaceship? There are several methods that researchers are pursuing, and each of them is interesting in different ways. One of them, the creative ways a spaceship can get artificial gravity, is the use of rotating habitats. How do rotating habitats work? Rotating habitats are spacecraft or modules that spin around an axis to create centrifugal force, which acts as artificial gravity for the occupants. However, creating artificial gravity on spacecraft using rotating habitats involves many technical and engineering challenges, such as designing and building large and complex structures, maintaining stability and safety, and minimizing energy consumption and cost. Here is how SpaceX can achieve artificial gravity on the Starship using rotating habitats. Determine the design parameters. The first step is to determine the design parameters of the rotating habitat, such as the shape, size, mass, material, rotation rate, and orientation. These parameters affect the amount and direction of artificial gravity, as well as the structural integrity and functionality of the rotating habitat. For example, the shape of the rotating habitat can be either torus-shaped, such as a ring or a wheel, or cylinder-shaped, such as a drum or a can. The size of the rotating habitat can range from a few meters to several kilometers in diameter. The mass of the rotating habitat depends on the material and the thickness of the structure. The material of the rotating habitat should be strong enough to withstand the centrifugal force and the space environment, such as radiation and micrometeoroids. The rotation rate of the rotating habitat determines the angular velocity and the centrifugal force. The orientation of the rotating habitat determines the direction of the artificial gravity and the exposure to sunlight. Calculate the artificial gravity. The second step is to calculate the artificial gravity that will be generated by the rotating habitat. The artificial gravity depends on two factors, the radius and the angular velocity of the rotation. The radius is the distance from the center of rotation to the point where the artificial gravity is measured. The angular velocity is the speed at which the rotating habitat rotates around its axis. choose the optimal rotation rate. The third step is to choose the optimal rotation rate for the rotating habitat. The optimal rotation rate should provide enough artificial gravity to prevent or reduce the negative effects of microgravity on the human body, such as muscle atrophy, bone loss, fluid shifts, vision impairment, immune system dysfunction, and psychological stress. However, the optimal rotation rate should also avoid excessive artificial gravity that can cause uncomfortable or harmful effects on the human body, such as increased blood pressure, heart rate, and body weight, reduced lung capacity and oxygen uptake, and increased risk of injury, fatigue, and pain. Moreover, the optimal rotation rate should also minimize the Coriolis forces that can cause disorientation, nausea, and motion sickness for the occupants. According to some studies, the optimal rotation rate for human comfort and health is between 1 rotation per minute and 4 rotations per minute, which corresponds to an angular velocity of between 0.105 radians per second and 0.419 radians per second. This range of rotation rate can provide an artificial gravity of between 0.1 g and 1 g, depending on the radius of the rotating habitat. For example, if a rotating habitat has a radius of 224 m, then it can provide an artificial gravity of 1 g at a rotation rate of 2 rotations per minute. If a rotating habitat has a radius of 894 m, then it can provide an artificial gravity of 1 g at a rotation rate of 1 rotation per minute. Launch and assemble the rotating habitat. The fourth step is to launch and assemble the rotating habitat in space. The rotating habitat can be either launched as a single piece or as multiple pieces that can be assembled in orbit. Launching the rotating habitat as a single piece can save time and effort, but it also requires a large and powerful launch vehicle, such as SpaceX's Starship, that can deliver a heavy payload to low Earth orbit. Launching the rotating habitat as multiple pieces can reduce the launch cost and complexity, but it also requires multiple launches and rendezvous, as well as complex docking and assembly procedures in space. The rotating habitat can be assembled either manually by astronauts or automatically by robots, depending on the size and design of the structure. Operate and maintain the rotating habitat. The fifth step is to operate and maintain the rotating habitat in space. The rotating habitat needs to be constantly monitored and controlled to ensure its proper functioning and safety. The rotating habitat needs to have a reliable power source, such as solar panels or nuclear reactors, that can provide enough electricity for the rotation and other systems. The rotating habitat needs to have a robust attitude control system, such as reaction wheels or thrusters that can adjust the orientation and stability of the rotation. The rotating habitat needs to have a durable heat shield and debris shield that can protect the structure from extreme temperatures and micrometeoroids in space. The rotating habitat needs to have a regular inspection and repair schedule that can detect and fix any damage or malfunction in the structure. Enjoy and explore the rotating habitat. The sixth step is to enjoy and explore the rotating habitat in space. The rotating habitat can provide a comfortable and stimulating environment for the astronauts, as well as a platform for scientific and educational activities. The rotating habitat can have different zones or sections that can serve different purposes, such as living quarters, working areas, recreational facilities, agricultural plots, or observation decks. The rotating habitat can have different features that can enhance the quality of life, such as windows, skylights, artificial lighting, ventilation, sound systems, or art installations. The rotating habitat can also have different experiments or demonstrations that can showcase the effects of artificial gravity on various phenomena, such as fluids, plants, animals, or humans. However, if SpaceX doesn't want to use rotating habitats, it can use another method called the centrifuge to mimic gravity on the Starship. A centrifuge, in its basic form, is a spinning wheel or cylinder that creates a centrifugal force, which pushes objects away from the center of rotation. This force can be used to simulate gravity by placing people or objects on the rim of the wheel or inside the cylinder. The faster you can spin the centrifuge, the stronger the force and the higher the gravity level. For example, if a centrifuge rotates at a speed that produces a force equal to Earth's gravity, then a person standing on the rim or inside the cylinder would feel as if they were on Earth. There are different types of centrifuges that can be used for artificial gravity on the Starship. One type is a torus, which is a ring-shaped structure that rotates around its axis. A torus can be large enough to accommodate living quarters, laboratories, gardens, and other facilities for the crew. A torus can also be connected to a central hub by spokes, which can allow access to other parts of the spacecraft or serve as elevators to change gravity levels. A famous example of a torus design is the Stanford torus, which was proposed by NASA in 1975 as a space colony for 10,000 people. Another type of centrifuge is a tether, which is a long cable that connects two masses and rotates around their center of mass. A tether can be used to link two spacecraft or modules and create artificial gravity by spinning them around each other. A tether can also be attached to an asteroid or a planet and use its gravity to stabilize the rotation. A tether can be flexible or rigid, depending on the material and design. A flexible tether can be easier to deploy and adjust, but it can also suffer from vibrations and oscillations that can affect the stability and comfort of the crew. A rigid tether can be more stable and robust, but it can also be heavier and harder to maneuver. An example of a tether design is the Nautilus X, which was proposed by NASA in 2011 as a multi-mission exploration vehicle with an inflatable centrifuge module. There is another type of centrifuge known as the carousel, which is a circular platform that rotates around its center. A carousel can be mounted inside a spacecraft or module and provide artificial gravity for a small area or activity. A carousel can also be combined with other systems, such as exercise equipment, medical devices, or entertainment devices, to enhance their performance and benefits. A carousel can be simple and cheap to build and operate, but it can also have limited capacity and functionality. An example of a carousel design is the artificial gravity device, which was tested by NASA in 2000 as a short-radius centrifuge for human research. The main advantage of using centrifuges for artificial gravity on spacecraft is that they can potentially reduce or prevent the negative effects of microgravity on the human body and mind. These effects include muscle atrophy, bone loss, cardiovascular deconditioning, immune system suppression, fluid redistribution, vision impairment, vestibular dysfunction, psychological stress, and cognitive decline. By providing a normal or near-normal gravity environment for the crew, centrifuges can help maintain their physical and mental health and performance during long-duration missions in deep space. Another advantage of using centrifuges for artificial gravity on spacecraft is that they can offer flexibility and diversity for the crew's activities and preferences. Centrifuges can allow different gravity levels for different purposes and situations, such as sleeping, working, exercising, relaxing, or recreating. Centrifuges can also allow different orientations and directions for the crew's posture and movement, such as standing upright, lying down, facing inward, or facing outward. Centrifuges can also allow different modes and durations of exposure to artificial gravity, such as continuous, intermittent, or variable. By providing these options for the crew, centrifuges can enhance their comfort and satisfaction during long-duration missions in deep space. However, using centrifuges for artificial gravity on spacecraft also has some disadvantages and challenges that need to be considered and addressed. One disadvantage is that centrifuges can introduce unwanted forces and motions that can affect the crew's perception and coordination. These include Coriolis forces, which are apparent forces that arise from rotating frames of reference and cause objects to deviate from their intended paths. Cross-coupled forces, which are forces that result from simultaneous rotations around different axes and cause undesired rotations. And precession forces, which are forces that result from changes in the angular momentum of a rotating body and cause changes in the orientation of the rotation axis. These forces and motions can cause disorientation, nausea, dizziness, vertigo, and motion sickness for the crew, especially when they move or change direction within the centrifuge, or when they transition between different gravity levels or environments. Another disadvantage is that centrifuges can increase the complexity and cost of the spacecraft design and operation. Centrifuges require additional mass, volume, power, and control systems to function properly and safely. Centrifuges also introduce additional loads and stresses on the spacecraft structure and components, which can affect their reliability and durability. Centrifuges also require additional testing and validation to ensure their compatibility and performance with other spacecraft systems and functions. Centrifuges also require additional training and procedures for the crew to use them effectively and efficiently. Another way to create artificial gravity on the Starship is to use the paragravity method, a hypothetical technique that does not rely on rotation or acceleration. Paragravity is a term coined by science fiction writers to describe a form of artificial gravity that is generated by some unknown means, such as advanced technology, exotic matter, or quantum phenomena. Paragravity would allow the Starship to have a constant and uniform gravity field inside its cabin, without having to spin or thrust. Paragravity would also avoid the problems associated with other methods of artificial gravity, such as Coriolis forces, cross-coupled forces, precession forces, structural stress, and energy consumption. How could SpaceX achieve paragravity on the Starship? There are several ideas that could be explored. One idea is to use magnetism to create a force that mimics gravity. Magnetism is a physical phenomenon that arises from the motion of electric charges and causes attraction or repulsion between objects. Magnetism can be used to levitate objects or people by creating a magnetic field that counteracts gravity. However, magnetism can also be used to simulate gravity by creating a magnetic field that enhances gravity. For example, if the Starship had a superconducting coil around its hull that generated a strong magnetic field pointing downward, then any object or person inside the Starship that had a magnetic dipole moment would feel an additional force pulling them toward the floor. This force would be proportional to the product of the magnetic field and the magnetic dipole moment and could be adjusted to match Earth's gravity.